In section 9.3, we're going to be figuring out how to solve quadratic equations. We're also going to be doing that in 9.4 and 9.6. The reason we're doing it in multiple sections is because there's multiple ways to solve quadratic equations. So I'm going to put the essential question down here, but then I'm going to go to my graphing calculator to give you a bigger picture of what we're going to be doing in this section and sections to come. So our main question today is going to be, how do I solve a quadratic equation by, and today, although I'm going to show you the graphs, you're never actually going to choose to solve them by graphing yourself. I do think it's worth me running through so you don't lose track of what you're finding, but our primary goal today is going to be this method right here, which is going to be called by using square roots. So we're going to take an algebraic approach. And before we even begin, so hold on there with your notes and just watch for a second. Before we begin, I'm going to explain the broad picture of what we're doing. I'm going to bring up my graphing calculator here. So we have what's called quadratic functions. They look like y equals ax squared plus bx plus c. And we've already graphed them, and we've already talked about how A controls whether it opens up or down, smile or frown. C moves it up and down the graph. B shifts the axis of symmetry. We've talked about how to find the vertex by doing negative b over 2a and plugging it in. We've applied it to some word problems. And now we're going to be doing what's called solving a quadratic equation. And when we solve a quadratic equation, we're actually determining what values for x make the function equal to 0. Keep in mind it makes the y value equal to 0. So having said that, I'm going to replace all those variables up there with some numbers so you can see what's happening. So suppose we have the quadratic function y equals x squared minus 3x minus 10. Alright, so this is a function that opens up. It makes a parabola. I could find its vertex. What we're going to be concerned with today is what we call the solutions. Alright, and the solutions are what make the function equal to 0. Sometimes we call those the roots of the equation. Sometimes we call them the zeros of the polynomial. But for our purposes in this class, we're going to be calling them the solutions. So we're really looking for what makes this function equal to 0. Well, let's do it graphically here so you can see what's going on. So I'm going to bring up a graphing calculator, and I'm going to go graph that quadratic equation. That's x squared minus 3x. Oops, got to get that minus in there. So let me insert a minus. X squared minus 3x minus 10. And let's talk about what we know about this right now. Because it leads in a positive, it's going to open up. If I wanted to find its axis of symmetry, I would do negative b, which would be negative 3, over twice a, which would be 3 over 2, or 1.5. So I know it's got an axis of symmetry at x equals 1.5. What I'm going to be concerned with today is what we call the solutions, which is where the y value is equal to 0. Well, let's go graph this to see what we've got going here. You can see, as indicated, or as I already said, that because the a was positive, I'm opening up. It's making a smile. You can see that axis of symmetry sitting right there at x equals 1.5. Those are things we already know from our previous knowledge. And what we're concerned with today is where does the function have a value of 0? Whoops, I clicked on there. Where's the function's y value equal to 0? Well, in terms of points on the parabola, again, right here, this is the point about 5, 4-ish, and this is the point whatever. All these are points along the graph. I want to know where the y value is equal to 0. Well, you can see that that occurs right here and right here on the graph. So really what we're finding algebraically is going to translate graphically into where that parabola hits the x-axis. it hits it at some point, comma 0. It's where the y is 0, and that's what we're looking for. And those are called the solutions to the quadratic equation. So in this particular one, I would say that its solutions, the place where it hits the x-axis, are over here at 5. So x equals 5 is a solution, and over here at -2. That's also a solution. What that means is if I put these two values into the given equation for x, a 0 will come out. So keep that in mind as we're doing these. Our ultimate goal in the next few sections is to determine what will give us a 0 out. Graphically, they're the x-intercepts. Now, why would that be important in a real-life situation? Well, let's go get rid of that calculator for a second. And so again, on this one, we said, this was the one I just graphed, we said the solutions were over at 5 and at -2. We could see that graphically, that's where it hit the x-axis or had a y value of 0. And just to run a little check on that so you understand the full details of it, we're going to put that in. We're going to get 25 minus 15 minus 10, which equals 0. I'm going to pause this for a minute. So as you can see, that when I put a 5 into the equation for x, I end up getting 0 out. That's why we call 5 a solution. And if I were to put -2 in, I'd also get a 0 out. So again, what we're doing here is we've got what's called, just to repeat, just so you get the big picture, we've got what's called a quadratic function. Its graph gives you a parabola. That's a graph of all the points that satisfy the equation. Sometimes open down, they sometimes open up. What we are now going to be doing is finding the solutions, which we want to know what x values causes 0 to come out. Graphically, what those are, if we put this on the x and y axis, is there these points right here, because on this x-axis is where the y values are 0. This is the point 1, 0, 2, 0, 3, 0, 4, 0, 5, 0. So if this were 3, 0, we'd call that. So that is what we're going to be looking for. And I'm stressing this because we're actually not going to be doing it by graphing, because graphing is the most inaccurate way to do it. We're going to be doing some other algebraic methods, but I don't want you to lose track of the fact that you are actually finding x-intercepts on the graph. So now let's continue with the notes here. So going a page forward. So again, we have our quadratic equation. A quadratic equation, again, is when we're equal to 0. A quadratic function looks like y equals ax squared plus bx plus c. We are going to be, again, kind of showing you a little bit graph, but our primary goal is going to be to do without graphing. So on here, let's take a look here what we've got. Move this over a little bit so you see it. To solve by graphing, we graph what we call related function. Are, just as I showed you, the x-steps, and I just went and graphed one for you. I showed you where it hit the x-axis. So on this one, this is the graph of y equals x squared minus 4. And it was put on a graph, and you can, again, use our previous knowledge that we know it looks like the parent function has just been moved down 4. And because of that, when I go graph it, what I've got here is what we'd call two x-intercepts, or two solutions. It's hitting at +2 and at -2. So we say those are solutions to the quadratic equation. Now, there can be one, let's underline that, two, or actually no solutions. And let's talk about why in terms of the graph. Again, the graph is really important for a deeper understanding, although we're not going to be doing a whole lot of graphing. There can be two solutions if the parabola hits twice. It can either open up and hit twice like on that one, or maybe it opens down and hits twice. But this would have two solutions. It can have one solution if the parabola only hits once. And if it only hits once, that means it must hit actually at its vertex right here. This would have what we'd call one solution. If that hit at the point, say, 3, 0, our solution is 3. So this, two solutions because it hits twice. This is one solution because it hits once. And finally, it's actually possible for you to have a quadratic equation that has no solutions. And that's if its turning point or its vertex occurs above the x-axis or below it and actually never hits it. So when it's above and it's opening up, I completely miss the x-axis, or if it's below and it's opening down, I completely miss the x-axis, which means I would have no solutions to the equation. All right, so let's move on to the next page here. And we're going to do a little bit of graphing. I'm not going to go to the graphing calculator. I'm just going to use my knowledge of what the graphs look like. So I'm going to graph what's called the related function, which means I'm going to look at y equals x squared minus 1. Remember, that's the parent function moved down 1. So instead of at 0, 0, it'd be at 0, 1. And it'd be at 1, 0. If we put a 1 in, a 0 comes out. Negative 1, 0, etc. So let's go and I sketch that out a little bit. And that's the graph. And it's got two solutions, one here and one here. That is where it's hitting the x-axis. So we say the solutions are x is equal to 1 and negative 1. And then we actually write that as plus or minus 1. And you can notice that there are two solutions on that one. This function right here is related function is y equals x squared. That's the parent function. It goes at 0, 0, 1 squared is 1, 2 squared is 4. We've graphed that one multiple times. That's this one. And its solution, or x-intercept, is right here. There is just one solution only. There's only one number in this world that when you square it, you get a 0 out. And that number is 0. So we'd say there's one solution and it's at x equals 0. So notice this one has one solution. The last one slid off my screen, so I'll go like that. Its related function would be x squared plus 1. It's the parent function moved up 1. So instead of at 0, 0, it'd be at 0, 1. Instead of at 1, 1, it'd be at 1, 2, and you could plug these in and graph them. But it looks like this. And you'll notice it never hits the x-axis, which means this one has no solutions. There are no solutions to this quadratic equation. It should make sense why. Because all numbers, when we square them, are positive, then if I add 1 to a positive number, there is no way I'm getting a 0 out. So that should make sense. It also should surprise you that all of these graphs are the exact same width. They're all the same width as the parent function. And again, that's because this lead number is a positive 1, positive 1, positive 1. Also, you'll notice that they're all opening up and making smiles because it's leading in a positive. So drawing on a lot of previous knowledge in here as well. So our next task, we're not going to do this right in here. Again, we're not going to focus a whole lot on the graphing. What I really want you to do is, let's cross this off. So I just really want you to understand that when finding the solutions, no matter how we do that, whether we do it graphically, whether we do it with algebra, whether we do it with a formula, we're going to be doing it with factoring, we're going to have multiple methods of finding the solutions, but it's really important that you understand that when you're finding the solutions, you are really finding the x-intercepts of the graph. I want you to note that tie-in. I want you to understand that in the real world, when we have quadratic functions, they're usually parabolic models are used for things that get launched or thrown or tossed or whatever. And again, what goes up must come down. And you can see that the solutions, or the x-intercepts, represents where it starts and where it lands. So it can be a pretty applicable part of a physics problem as well. So I'm going to make another video where I actually show you how we find these without looking at the graph. So you'll have to log in and watch that for the rest of the page, which starts on the next page. So this section will be in 2 videos.